This is a video solution for part B of problem 6 from Superquiz 2. So this is another initial value problem. So here we're given, hey, just a first order differential equation. Only on the right hand side, the forcing function is not given to us explicitly. We're told it's actually given in the graph, which is over here on the right. So in order for us to compute a solution to this differential equation, we're going to have to write down an explicit form for this function g of t. So we'll notice it starts off by just being 0 up until you get to t equals 2, and then the function turns on. Okay. So as soon as we see behavior like this, we should be thinking about using a unit step function. Then we see, okay, it's going to turn off at 4, but then turn back on to some constant function 6 when you get to t equals 4. All right, so let's give this a try. We're giving this a try here with, let's see, g of t equals, so we're going to turn on at 2. So let's put in a unit step function, a u2 of t. So that tells us turn something on. And then we're going to want to have this line segment going from 2 to 4. So let's see what this line segment is. We can see from 2 to 4, it goes up from 0 all the way to 8. All right, so the rise is 8, the run is 2, so it has a slope of 4. So this almost looks like y equals 4t. Okay? Only it's not y equals 4t, because y equals 4t would go through the origin. Instead, we've shifted it over to the right by 2. So I can fix that. Let's get this parenthesis right. I can fix that by shifting the t by 2. So that's what I want to turn on at u2. Okay, I want to have a 4 and then a t minus 2. Okay, now what's going to happen when we get to 4? So at 4, we're going to turn something else on or off. So first, we want to turn off this line segment that we have going up. So we'll do a minus 4t minus 2. Then we also want to turn on this constant function, which has height 6. So we'll add 6. All right. So I think it's maybe going to be helpful to distribute at least this bottom one here. So we'll keep this top one, u2 of t. Why by the way, do I keep it? Well, I usually like to have a shift that matches the number in my unit step function. So since I already have 4 times quantity t minus 2, I might as well leave that there for now. All right. For the u4, again, I probably want to have some shift by 4. So let's see what we have. I have a negative 4t, and then negative 4 times negative 2 is 8. 8 plus 6 is 14. So I'll do this in 2 steps maybe. So I have negative 4t plus 14. Now, I don't want to leave it this way, right? I want to have a shift by minus 4. So we'll copy our u2. And I'll move this 4 to the front. That's kind of bothering me. Plus, okay, I have a u4. Now, instead of a t, I want to have a t minus 4. So I'll put here negative 4 t minus 4. If I did this, I would have negative 4 times negative 4 is 16, right? Positive 16, but I only want positive 14. So I'm going to have to subtract 2 away. Okay, so now I've written each of these pieces as a unit step function times some shift of t, right? Or some function of t shifted by the same point where we're turning the step function on. All right, so maybe we'll just have to copy this up here. So our g of t is equal to, we said 4 u2 of t times t minus 2 plus, and we have a u4 of t times negative 4 t minus 4 minus 2. Excellent. So now we actually know what the forcing function is, and so we can apply the Laplace transform. So when I apply it to the left-hand side, I'm going to get S times, well, let's see, we have the derivative of y. So this will just be Ly minus y of 0, and y of 0 is 3. Okay, minus 2 times the Laplace transform of y. Okay, on the right-hand side, well, we're going to take the Laplace transform. Okay, the 4, we don't worry about that for the moment. But what do we have? We have a unit step function times a function shifted by the same point we're turning the step function on. So at this point, we can use the second shifting theorem, and we'll get 4 times e to the negative sc, where c is where we're turning the step function on, so negative 2s. And then we need the Laplace transform of the underlying function, right, which has been shifted. So this function has been shifted by 2. Before we shifted it, remember we thought it was a, well, 4t, but you ignore the 4, right? We thought it was a t. So we just need to take the Laplace transform of t, okay, which we know is 1 over s squared. Okay, now we go to the second summand, and again we have a unit step function times some function, right? Maybe it's a little trickier to see here, but this original function, right? So this is some function which has been shifted by 4. The original function, f of t, was negative 4t minus 2. Okay, we just see we replace the t minus 4 with a t. Okay. So, again, using the shifting theorem, u4, that part we know is going to turn into the exponential e to the negative 4s. And now we need to find the Laplace transform of negative 4t minus 2. So the negative 4 we can just leave. Laplace of t is 1 over s squared. So we'll get negative 4 over s squared. And then the minus 2, we'll just imagine it was a 1, and then we'll at the end multiply by negative 2. The Laplace of 1 is 1 over s. So this will be minus 2 over s. Okay, so we've applied the Laplace transform to this differential equation. Now we want to solve for L of y. Okay, this is pretty easy. On the left-hand side, how many L of y's did we have? Well, we have s minus 2. All right, I don't want this minus 3, so that'll get moved over to the right. So I have 3, and then all the rest of this stuff. All right, so we have 4e to the negative 2s over s squared. And then, well, we could distribute this. So I have minus 4e to the negative 4s over s squared, and a minus 2e to the negative 4s over s. Okay, again, we're trying to solve for Ly, so we can divide by s minus 2. So we'll divide here by s minus 2, which is going to be okay to do. S is not going to equal 2. So Ly is going to equal, all right, so we have 3 over s minus 2. We have 4e to the negative 2s over s minus 2 times s squared. We have minus 4e to the minus 4s over s minus 2 times s squared. And we have minus 2e to the minus 4s over s minus 2 times s. Now, at this point, we would like to take the inverse Laplace transform. And, well, I mean, of course, we can, except on the right-hand side, they're not really all in the form yet we would like. Right? I mean, this first guy is okay, right? We can see something pretty similar to this in the table. But these ones with this product on the bottom suggest we're going to want to do a little more prep work using a partial fraction decomposition. Okay, so in each of these cases, we're going to have s minus 2, and then we're either going to multiply by s squared, actually in both of these, Okay, except for this last one, which just has an s. So let's go down and do some partial fraction decompositions, do a little, like I said, prep work. So we'll jump down a little bit. So first, we want to do a partial fraction decomposition for 1 over s minus 2 times s squared. So this will have an s minus 2 component, it will have an s component, and it will have an s squared component. Okay, and we get constants on top of all. All right, let's see. If we clear denominators, then we have 1 is equal to a times s squared plus b s times s minus 2 plus c times s minus 2. All right, if I'm able to get rid of a couple components, I like to do that. So let's see. If I make s equal to 2, that will annihilate the second two summons. So when s equals 2, the left-hand side is still 1, and the right-hand side would be a times 2 squared, which is 4. Okay, so a is going to equal 1/4. Okay, also though, if I make s equal to 0, that will annihilate the first two components. So when s is equal to 0, then again the left side is 1, but the right-hand side will just be c times 0 minus 2, so negative 2c. And so c is equal to negative 1/2. All right, let's put those into our decomposition. Okay, we can even put them over here if we like. 1/4. Okay, this becomes minus 1/2. All right, now we want to get b, and there's no way to isolate it using the above trick in the sense that we can't just annihilate the other two pieces. But we can just distribute a little bit to get b. Notice the first term here, when I distribute, would be bs squared. And let's see, on the left-hand side, I have no s squareds. So no s squareds on the left. And on the right-hand side, I have a fourth s squareds. And I also have bs squareds. And that's it. There's no more s squareds. And so b plus a fourth has to be 0. So we conclude b is negative a fourth. Okay. Cool. So we can go back up and rewrite our, it'll be actually the second and the third summands, right, using this decomposition. So we have 3 over s minus 2, that'll just get copied. Now, this 4e to the negative 2s, that's just going to hit every single one of these three pieces. So let's see, we have a 1/4 times the 4, that's pretty good. So e to the negative 2s over s minus 2. And then the second one, okay, negative a fourth times 4, so we'll get a minus e to the negative 2s over s. And now let's see this next one, 4 times negative a half is minus 2. So we'll have minus 2 e to the minus 2s over s squared. Okay, now we get to do it the same thing with this third summand. And let's see, negative 4 times 1/4 is minus 1. So we'll keep going down here. So we have minus e to the negative 4s over s minus 2. Then negative 4 times negative a fourth is going to be just positive 1. So plus e to the negative 4s over s. And then we have negative 2 times negative 4 times negative 1/2, which is going to be positive 2. So plus 2e to the negative 4s over s squared. Okay, now there's going to be more. We're not quite done because we have to break up this last piece, but that has a different partial fraction decomposition. So we want to know the partial fraction decomposition when the denominator is now s minus 2 over s. So let's head back down. So we have 1 over s minus 2 times s. And I'll use some different letters now. We'll use d over s minus 2 and e over s. Okay, so we can clear denominators, and we get 1 equals ds plus e times s minus 2. And we can play this really nice game where if we make s equal to 2, that'll annihilate the second sum end. So when s equals 2, we get 1 equals 2d, and so d equals 1/2. And if we make s equal to 0, that'll annihilate the first sum end. So 1 will equal to -2 times e. And so e will equal -1/2. All right, so our d here was 1/2, and our e is -1/2. Okay, so, well, we can't see that too well, so let me do a little quick copy, just so we have that in our mind. All right, so let's just copy it into here as a quick reminder. So at this point, we can now multiply out this 2e to the -4s times this partial fraction decomposition we have. So first, okay, we have, it's really -2 times +1/2. That'll be -1, so minus e to the -4s over s minus 2. And then we have -2 times -1/2. That'll be +1. So plus e to the -4s over s. Okay, and there's some simplification that we can do here, because you'll notice, for instance, if we look in this column, we have actually the exact same thing. And then in this column, right, these two pieces are exactly the same thing. All right, so let's try to simplify just a little bit. So we have 3 over s minus 2, and then we have an e to the -2s over s minus 2. We have a minus e to the -2s over s. We have a minus 2e to the -2s over s squared. Then, okay, we have -2 of these, so minus 2e to the -4s over s minus 2. And plus, now we have 2 of those, so plus 2e to the -4s over s. And then finally, plus 2e to the -4s over s squared. Okay, so that's our L of y. And now what I claim is that each one of these is in the position we need it to be in order to use the table to compute the inverse Laplace transform. So let's get to it. So we now have that if we apply the inverse Laplace transform, so remember this was all equal, right, to Ly, right? Well, that was a long time ago. That was our Ly. So when we take the inverse Laplace transform, we get y. Okay, now how about on this long right-hand side? Well, first, this is just going to be the Laplace transform of e to the 2t times 3. So we get 3e to the 2t. All right, now the second one, if you didn't have this exponential, you'd say, okay, that's just 1 over s minus 2. That would be the Laplace again of e to the 2t. Okay, but we have this exponential, and what we know by the second shifting theorem is that this then corresponds to if you'd taken the Laplace of the unit step function, right, which is now, okay, we'd be shifting by 2. We would take the unit step function, so that would be u2 of t, right? And then we would multiply it by, well, let's see, which function, we said this was 1 over s minus 2, actually that actually comes from the function 1 over s. Is that right? Nah, that's not right. That's not what we want. Now, what we really want is just to recognize 1 over s minus 2 is the Laplace of e to the 2t. And so by the second shifting theorem, we would need to take e to the 2t, so e to the 2t, and replace the t by t minus, well, whatever the shift was. The shift here is 2. Okay, so now we go to the next one. And we say, okay, this is, minus, okay, it looks like 1 over s, which would be the Laplace of 1. However, there's this e to the negative 2s, so again, we're going to get a u2 of t. So let's see, we have minus u2 of t times, right, the original function shifted by 2. But the original function, right, what gave us 1 over s? That was just 1. You can't shift that by 2, so this is just times 1. Okay, next one. Again, you have the exponential, so that's going to be a unit step function at 2. So let's see, we have minus 2 u2 of t. And then the remaining function is 1 over s squared, which we know is the Laplace of t. So we need to take t and shift it by 2. So we'll have t minus 2. Okay, now we go down to this second line. And okay, again, we're going to have a unit step function, but this time starting at 4. So we'll have minus 2u4. And the remaining function is 1 over s minus 2. So again, that comes as the Laplace transform of e to the 2t. We need to shift the t, in this case, by 4, right? Because that's our unit step function. Okay, next one, same idea. We'll get plus, okay, again, there's a 2, u4 of t, and now the remaining function is 1 over s. So that came as the Laplace of 1, so no shift needed. And then same idea down here as we had up here. So this will be plus 2 u4 of t. And again, this is the Laplace of 1 over, well, 1 over s squared is the Laplace of t. So we'll shift the t this time by 4. Okay, and so we can do a little bit of factoring, but nothing super special at this point. How many u2 of t's do we have? We have e to the 2 times t minus 2 minus 1 minus 2 times t minus 2. Okay. Again, maybe you could simplify this a little bit, but we don't want to worry about those things. And then we have a u4 of t component. And how many u4 of t's do we have? We have negative 2 e to the 2 times t minus 4. We have 2 times 1, and we have 2 times t minus 4. Okay, and that's a pretty decent place to stop, knowing you could do a little bit of arithmetic, but we don't want to.